So welcome to Math 350, lecture 32, polar, cylindrical, and spherical integrals. So we are at the home stretch, and we are now doing one of the main techniques of multivariable calculus, doing multiple integrals. And there are a couple of very standard situations where the coordinate systems are so useful. We've given them names, and we do a lot of work with them because they occur all the time. So these are the polar, cylindrical, and spherical. We talked a little bit about polar last time. And the big thing to remember is how do you convert from dx dy to dr d theta? And what was nice is there was a conversion factor, but it was the same conversion factor no matter where you were. It was always just the conversion factor was just r. So, well, okay, so it's not the same. It depends on the radius. It doesn't depend on the angle. So we have a very simple formula. When we do cylindrical, when we do spherical, how do things convert in those cases? So we've talked a little bit about these in the past. So, one of the nice things about the web is I can just cull some pictures and not have to try to draw things. So, polar down below, here's the r, here's the theta. Everybody agrees on the letters to use for polar. For cylindrical, it's still r theta, and now we add a z. And so if you try to think about a little volume element in spherical, you're going to have, your little element from polar, and now you're going to give it a little bit of a thickness. And what's that thickness going to be? So what would the thickness be? Not z, close. Z would be like a big number. You need a small number related to z. dz, delta z, something like that. So, we go from dx, dy, dz to r, dr, d theta, dz, or if you want, dr times r d theta times dz. Here, that's a good way to look at it. I want a product of three lengths. D theta is not a length. R d theta is a length. It's that small little infinitesimal arc. Spherical is a little bit harder. So we have our coordinates. We have, rho, theta, and phi, and the mathematicians and the physicists have slightly different conventions in terms of which do they use. So who are my physicists here? Okay, do you use theta coming down from the z-axis? Okay, and what do you use?
It didn't matter.
It doesn't matter, but which do you use? You've got to be careful so that you know. So which are you using? So you're using theta coming down from the z-axis, or you're using theta in the xy plane? So which is coming down from the z-axis? So you have theta coming down from the z-axis?
Yeah.
Okay, so you're using the opposite of what we're using here.
Yeah.
Yes.
You also said it matters.
It doesn't matter so long as everybody knows. Unfortunately, the conversion factor dx, dy, dz to d rho, d theta, d phi, it has a dependence on theta but not phi, or phi but not theta, depending on which way you do your items. So you will get a different answer if you make a mistake like this. We have to be careful. It does not matter what letter we use, but you've got to be careful that different books will use different letters. And if you just naively quote a formula, you might actually use the wrong formula. I learned it in my physics class before my math class, so I have to constantly fight to use phi coming down from the z-axis. It is hard for me. Why do mathematicians do this? These are the people who gave you cosecant is 1 over sine and secant is 1 over cosine. There is a reason for that notation. It sounds foolish at first, but there is a reason as to what is the co of an angle. And if you think about it, this should be a good choice for things. Why do mathematicians do this? They want things to reduce to the xy plane. They want it to reduce to the polar coordinates. And so if we do it like this, now that we're in the, once we come down phi radians from the z-axis and now we start turning around, it's now just like we're doing polar coordinates. And that's why we use rho. The reason physicists often use theta coming down is frequently it's the theta dependence that really matters, not the phi dependence. You often have things that are independent as you rotate about the XY plane. And so they focus theta to be the variable that's more interesting. We'll just try to draw things again, very, very poorly. Here's X, here's Y, here's Z. And we come down. So here is my radius rho. I'm coming down some angle phi. And the first thing I do is this over here, this Z is going to be rho cosine of phi. And this I'm going to call R is rho sine of phi. And now I can spin in a circle parallel to the XY plane. And so in that circle, I'll just try to draw it again over here. I'm above the XY plane. Oops. And then what I can do is that will be my angle theta. And so if I want to look at what is the distance I travel here, if this is R, this is going to be R d theta. If I do a small little change in angle. So if I do like a little d theta like that. If I want to figure out like an infinitesimal arc. But what is R? R is rho sine phi. So the infinitesimal arc is going to be rho sine phi d theta. Okay. And so when I'm trying to figure out what's going on, if I want to look at, how does dx, dy, dz transform? What I'm going to do is I'm going to have my radius rho, and then I'm going to move it up a little bit, delta rho. And then I'm going to come down a little bit like this. Here's my phi coming down like this. And so if I want to do a small little arc over here, this would be rho delta phi. And this is giving me 2 of my 3 directions. And my third direction is now moving in that circle. I have my circle coming around here. So my third direction coming in like this is going to be my R d theta, which is going to be rho sine of phi d theta. So when I put it all together, I get dx, dy, dz is going to become d rho times rho d phi times rho sine of phi d theta. And when I write it like that, you can see it's 3 lengths. No one ever writes it like this. You always have the d rho d theta d phi, d rho d phi d theta all together, and you put everything else in front of it. So this is the same as rho squared sine of phi d rho d theta d phi, or rho squared sine of phi, oops, d rho d phi d theta. Doesn't really matter which order you do it. So that's the most important thing to remember. It's how the volume element changes. The dx, dy, dz becomes rho squared sine phi d rho d theta d phi. The rho squared should be obvious. I need a volume. What are the units for volume? So if I give you a volume, what should you be thinking of for the units of a volume? I'm sorry? Cubic what? Cubic meters, say. So if rho is in meters, d rho is going to be in meters. That's great. But d phi is not in meters. Rho d phi is in meters. D theta is not in meters. Rho d phi is in meters. So the rho squared is very natural. That's going to give me now a volume. The sine of phi, that's harder. And the reason we have a sine of phi is if we look at the circle we have, parallel to the xy plane, the radius has been reduced a little bit. Now, if you think about it, where is the radius reduced the most? For which value of phi is the radius going to be smallest? Zero. So when phi is equal to 0, we're very close to the z-axis. If we move down a small little bit, it's going to be a very small radius. Where is the radius going to be largest? Where's r going to be largest? Around pi halves. And so it tells us that this little volume element is going to depend on how far down we're coming from the North Pole. If we're very close to the North Pole, the volume element is going to be smaller than if we're close to the equator. Okay, and again, it just comes down to how we've parameterized and how we've chosen our variables. And so now, if I want to do an integral, say over the 0 less than equal to x squared plus y squared plus z squared is less than equal to r of f of x, y, z, dx, dy, dz, this would become the integral. Then it would be, now we have to remember, how does everything change? So z was equal to rho cosine of phi. And remember, we had r was equal to rho sine of phi. X is r cosine theta, so that's going to be rho cosine theta sine of phi. Y is r sine of theta, so it's going to be rho sine of theta sine of phi. And so now I just substitute this in for my function. It's going to be f of x, which is rho cosine theta sine phi, y, rho sine theta sine phi, z, rho cosine phi. Then it's going to be rho squared sine of phi d rho d theta d phi, if I do it in that order. So phi goes from theta, goes from rho, goes from. So rho goes from 0 to r, theta goes from 0 to 2 pi, and phi, you have to remember, only goes up to pi. So we go from North Pole to South Pole, and then we spin around 2 pi radians of 360 degrees. So we don't have to have phi going from 0 to 2 pi. And now I've set up my function for integration. And then it just comes down to, can we actually evaluate this integral? Yes.
Should the or the side or rho side?
No. Because if you look at the picture when you're coming down, phi is the angle coming down from the z-axis. So the z is the adjacent side. So it's going to be rho sine phi. And then the reduced radius, r, is going to be rho sine phi. So the z is just going to be rho cosine phi, because it's looking at like the projection onto the z-axis. And so all we have to do now is just take our function and replace x, y, and z with stuff like this. Now, hopefully, we're in a situation where f depends maybe only on x squared plus y squared plus z squared. If it depends only on x squared plus y squared plus z squared, then these integrals become very easy to do. Or maybe it depends on x squared, y squared, z squared, and phi, but it doesn't depend on theta. So the hope is that you have something that becomes nice. A lot of times you have the ability to choose your coordinate systems to try to make things convenient. Maybe we'll do this problem later. It is one of the most important integrals in all of mathematics and physics. Imagine I have some massive mass and I have a point. And I want to show that the force of the mass on the point is the same as if all the mass was concentrated at the center, right? If you're doing physics, this is the big problem. that I want to be able to show that all the mass can be assumed to be at the center. And if you want, you can assume that your object has uniform density just to make life easier. Okay? Where should we, without loss of generality, where do you want to assume that point is? I'm sorry? This other point? We can't put the point that's outside the circle, but I can choose my orientation of my axes. How might you orient your axes? Where do you want that point to be? It's got to be above some point on the sphere. Which point do you want it to be above? Well, in some sense, every point's above the center, because you can draw a line from the center along the z-axis. So without loss of generality, why not just assume that it's just above the North Pole? And then what you want to do is you would then need to figure out what is the force on it from every point. Well, we know by symmetry that any point I have over here is going to yank it in this direction. There's a complementary point over here which yanks it in this direction. So the net yank is always going to be straight down. So we know that the net force is going to be in the direction of the line connecting the point to the center of the sphere. We don't know the magnitude. And we would have to go through and try to do the calculation. And you get a different answer depending on whether or not the point is inside the sphere or not. You might have proven in physics that if you have a hollow shell and you have a point inside a hollow shell, there's no force. Everything cancels out beautifully. So we might do this problem later. It's a really good, painful integral to do. If we do it, it is a lecture that I'm not going to prepare because it's painful enough to do it once. I don't want to do it twice in a day. But it's one of the most important integrals in all of science. It allows us to say that when we're trying to do these problems in orbital mechanics, we can assume all of the mass is just at one point. Oh, that's much nicer than worrying about everything. And I think on the first day of the semester, we actually talked about trying to approximate a sphere with a collection of points and seeing what happens as we take a finer and finer mesh. Does this converge to having all the mass at the center? It looks that way, but there are other things, and if you're doing physics, you've seen special relativity, where things look like they might be behaving in a certain way, but as we get more accurate measurements, we see that it's not. So, as a nice exercise, if you want, try to set up the calculation to determine what is the force on a point above the North Pole to a mass with uniform density. And see if you can show that you may assume that all the mass is at the center. We can easily calculate what the force would be if all the mass is at the center. It's just g m1, m2 divided by the square of their separation. Okay, so let's try to do some integrals. So let's say I want to integrate over, say, a sphere of radius r. And let's say I give you the function e to the negative x squared plus y squared plus z squared over 2 dx dy dz. So any thoughts about how we should do this integral? Do we want to integrate this in Cartesian? Let's try again. No, right. Let's just see how bad it would be to set this up in Cartesian. So this is, x squared plus y squared plus z squared is less than or equal to r squared. So it would be x goes from minus r to r, y goes from minus the square root of r squared minus x squared to the square root of r squared minus x squared. And then z goes from minus the square root of r squared minus x squared minus y squared to the square root of r squared minus x squared minus y squared, e to the negative x squared plus y squared plus z squared over 2 dz dy dx. And so what's particularly nice about this problem is it should look completely hopeless. We don't have a nice antiderivative for the exponential function. So we can't even write down the antiderivative. And we have bad bounds of integration. Yes. So we need to integrate a sphere. So the first is if I fix x and then I fix y, I then have to ask, what can z go from? So if I fix x and y, well, z squared, the largest it can be is r squared minus x squared minus y squared. And the smallest it can be is the negative of that. You want to take the square roots. And then once I fix x, what's the largest y could be? Well, the largest y could be is, for given value of x, if z equals 0, how large can things go? Another way of looking at it is, let's do it one at a time. Let's take x. So if I forget about y and z, the smallest x could be is negative r. The largest x could be is positive r. So x is going from minus r to r. Once I choose x, once x is fixed, now I need to figure out what's the range of y and z. Well, once x is fixed, bring it over, look at r squared minus x squared. And now what's the largest y could be? The largest y could be is when z equals 0. And that's how we're going to get these bounds. And then we can just keep going like that. I could split things up a little bit. I could write the exponential as a product of 3 exponentials. But this should show you, the hopelessness of this problem. We don't have an antiderivative, right? And the region of integration is bad. Neither one is good. So we should not spend much time trying to calculate this integral. So what should we do? How do you think we should evaluate this triple integral?
If you multiply the exponential by x squared and then you have y squared, those add up.
So I mean, we could write this as e to the negative x squared plus y squared plus z squared over 2. This is e to the negative x squared over 2, e to the negative y squared over 2, e to the negative z squared over 2.
Yeah.
We could absolutely try that, but unfortunately, neither one of these has a nice antiderivative. And we talked about how we don't have a nice antiderivative for that. So how should we do this integral over a sphere? Convert it to spherical coordinates, right? If I give you an integral over a sphere, what should be your go-to? Spherical coordinates. If I give you an integral over a cylinder, what should your go-to be? And if I give you an integral over a circle, your go-to should be polar coordinates. It should be the first thing you try. So I've talked about the baby method of mathematics. Baby is crying. Why is baby crying? What can I do to make baby happy? After a while, you start to have a sense of which things to try first. Whenever you see a sphere, your first thought should be, let me convert it to spherical coordinates. And so we convert to spherical, we would have integral, integral, integral. Now we have e to the negative x squared plus y squared plus z squared over 2. What is x squared plus y squared plus z squared in spherical coordinates? So in spherical coordinates, what would x squared plus y squared plus z squared equal? So, going back, this is something we did early in the semester. You've got to remember this. If z is rho cosine phi, x is rho cosine theta sine phi, y is rho sine theta sine phi, get x squared plus y squared plus z squared, if you do the algebra, is rho squared. So what is a sphere? A sphere is all points a fixed distance from a center. So if I'm giving a circle, of radius 1, I'm an object in a plane, all things that are 1 unit from the center. If I give you a sphere of radius 1, it's all things that are 1 unit from the center. So over here, if you square everything out, x squared is going to be rho squared cosine theta squared sine phi squared y squared is going to be rho squared sine squared theta sine squared phi. Oh, cosine squared plus sine squared is 1. So you'll get rho squared sine squared phi, rho squared cosine squared phi. The cosine squared and the sine squared cancel. So if you're a little bit uncomfortable with this, you have to just review the spherical coordinates we did earlier in the semester. We were putting some material in the bank. Now is the time when it's going to pay dividends. So x squared plus y squared plus z squared is rho squared. So the idea is that for many problems, if they only depend on the square of the distance, then the coordinate change is going to become very nice. And so now we're going to e to the negative rho squared over 2, and then dx dy dz becomes rho squared sine phi d rho d theta d phi. So phi goes from 0 to pi, theta goes from 0 to 2 pi, and then rho goes from 0 to capital R. So when you look at this, this is really 3 integrals. Can we split it as a rho integral times the theta integral times the phi integral? Yes, because the integrand factors. What is the integrand? This is the integrand. I can write this as, a of rho times b of theta times c of phi. I can split it up nicely. I don't have this nasty, say, e to the negative rho theta. Ugh, that would be horrible. So what would a of rho be? So what would a of rho equal? So I'm claiming I can write this as a product of 3 functions. One function depending only on rho, one function depending only on theta, one function depending only on phi. What's the function over here? What would be my a of rho? I'm sorry? Perfect. So somebody else want to give me what b of theta would be? This is the hardest one. It's just 1. And what would c of phi be? It would just be not 1. Sine of, sine of what? What would c of phi be? Sine of, you have to speak loudly. Sine of phi. And so I can write it as 3 functions that don't see each other. And so because of that, I can now write this as this is going to be the integral phi goes from 0 to pi of sine of phi d phi times the integral theta goes from 0 to 2 pi of 1 d theta times the integral rho goes from 0 to r e to the minus rho squared over 2 rho squared sine, rho squared d rho. So the first one, what's the integral of sine? I'm sorry? Negative cosine. And I'm evaluating this at pi and at 0. So I will let you do the calculation later. You get that this integral is equal to 2. What do I get when I integrate 1 from 0 to 2 pi? Two pi. And now I'm left with the integral rho goes from 0 to r e to the minus rho squared over 2 rho squared d rho. And the question is, what is that integral? But I've reduced this terrible 3-dimensional integral to a very nice 1-dimensional integral. I can approximate this with a Riemann sum if I need to without too much trouble. I've gone from a 3-dimensional problem to a 2-dimensional problem, to a 1-dimensional problem. Is this a nice integral to do? I'm sorry? If I change the exponent of 2 to a 1, would it be nice? Yeah, then I could do a U substitution. So what I'm going to do now is I'm going to introduce a special function that does occur a lot in mathematics and physics. We've actually already seen this when we did the baseball lecture. So gamma of S is defined to be the integral from x goes from 0 to infinity, e to the minus x, x to the s minus 1 dx, which is the same as the integral x goes from 0 to infinity, e to the minus x, x to the s, dx over x. And I'm just doing this to give you a sense of why the hell would you define it with s minus 1 and not s? It's because we actually like to look at it as dx over x. If I change x by a factor of 5, dx over x doesn't change at all. The top changes by a factor of 5, the bottom changes by a factor of 5. It turns out for some problems, this is a better thing to be integrating with. Whenever you see an integral, you should ask, does the integral converge? Well, for the integral to converge, it needs to have good decay. And so one of the reasons I want to do this problem, and I want to do this function today, is this is a chance to review some of your calculus. And given that we have an exam coming up, this is not a bad time to review some of these things. So we want to make sure the integral converges. So I claim integral converges if the real part of s is greater than 0. You could, if you want, just consider s to be a real number and just say, I want s to be greater than 0. It turns out you can make sense of this when s is complex. We're not really going to do that in this class. When you look at this function, there are two dangers. So danger near 0, danger near infinity. If I want a function to be integrable, it has to have good decay at infinity. Well, when x gets really, really large, x large, integrand looks like e to the negative x times x to the s minus 1, which is x to the s minus 1 over e to the x. Any power of x grows much, much slower than the exponential. Does anybody know what rule we could use to prove this? So my daughter says, take it to the L'Hopital, right? So if we say, give me a big integer. 47, okay. So let's look at the limit as x goes to infinity of x to the 47 minus 1 over e to the x. Take it to the L'Hopital. So we have infinity over infinity. So how do we evaluate infinity over infinity? We take the derivative of each. So this is the same as the limit as x goes to infinity. We would have 46 x to the 45 over e to the x. And we do this a lot of times. And eventually we'll get 46 factorial over e to the x, which goes to 0. This shows you x to the 46 over e to the x goes to 0. The e to the x goes faster. So if I give you, the integral, if I take, say, s equals 44, e to the negative x times x to the 44 minus 1. If I want to compare that, this would be e to the negative x, x to the 47 minus 1 divided by x cubed, right? And this will be less than or equal to 1 over x cubed if x is big. So this means it's going to decay fast enough. 1 over x cubed, that's integrable. So this is one way to show that the function is integrable, is I'm using essentially a comparison test. And again, this is a way to try to review a lot of the material we've done throughout the semester. If I want to show something is integrable, if I want to show something converges, I want to compare it to something I know. We talked about p series, the sum of 1 over n to the p. that converges if p is greater than 1, diverges if p is less than or equal to 1. So if I had something like, s equals 44, well, I know if I put in 47, I can then divide by x cubed. And so this whole numerator is going to 0. So eventually it's going to be less than 1. And it only matters what goes on for very large values. It doesn't matter for small values. So for really large values, the numerator is going to be less than 1. The denominator is like x cubed. And if I integrate x cubed, that's going to be finite. So I know there's no problem as I go to infinity. Where's the only other place where things might blow up for the integral? One is going towards infinity. The other is near 0. We've got to make sure things don't blow up. Near 0, we have e to the negative x times x to the s minus 1. Now, by Taylor series, e to the negative x is 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus dot, dot, dot. So when x is close to 0, what is this approximately? Good, it's close to 0. It's approximately 1. So near 0, e to the negative x times x to the s minus 1 is approximately x to the s minus 1. So if I integrate from 0 to some small epsilon, of e to the negative x, x to the s minus 1 dx, that's approximately integrating from 0 to epsilon of x to the s minus 1 dx. When is that going to be integrable? Well, my problem is if s minus 1 is a negative number, it blows up. If s equals 0, we get the integral from 0 to epsilon of 1 over x dx. What function has derivative 1 over x? ln of x. So it would be the natural log of x at 0 and epsilon. So this is the natural log of epsilon minus the natural log. This is infinity. So if s is equal to 0, it blows up. If s is greater than 0, we get the integral from 0 to epsilon of x to the s minus 1 dx. This is going to be x. We add 1 to the s over s at 0 and epsilon. And that's going to be epsilon to the s over s minus 0, and it's finite. So as long as s is greater than 0, this integral is going to be finite. So again, this is a chance to review some of our stuff on convergence of series, convergence of sequences. We're doing a comparison test. I know the harmonic series 1 over n. That's one of my go-to what diverges, harmonic 1 over n. So if I take s equals 0, I've got x to the negative 1, that blows up. Okay. Now, we have gamma of s is the integral from 0 to infinity of e to the negative x, x to the s minus 1 dx. Can somebody give me a good choice of s? When you look at this, what's the nicest s that leaps out at you? 1, right? So if you take s equals 1, you've now got gamma of 1 is the integral from 0 to infinity e to the negative x dx. That's just negative e to the minus x at 0 infinity. So that's e to the negative x at 0 infinity. I get to flip the order of integration with the minus sign, and I just get 1. Building on our success, what's the next number to choose? 2. So this is a chance for us to practice our integration. Gamma of 2 is the integral from 0 to infinity e to the negative x times x dx. How should we integrate this? Sorry? By parts. So we have to choose, what do we want u to be? What do we want dv to be? Do you want u to be x, or do you want u to be e to the minus x? X, because if we have u be x, then du is going to lower the polynomial. So u is x, du is 1 times dx, dv is e to the negative x, v is going to be negative e to the minus x. There's a dx there. So gamma of 2 is equal to uv at 0 infinity minus the integral from 0 to infinity of v du. So we get uv, which is going to be negative x e to the minus x at 0 infinity, plus the integral from 0 to infinity of v du, which is e to the minus x dx. Well, when I put in 0 and infinity for the boundary term, when I put in 0, I get 0. When I put in infinity, I get infinity times e to the negative infinity. How do you evaluate x times e to the minus x? What do you do? We've got infinity. When we put in infinity, we would have the limit as x goes to infinity of x e to the negative x. This is the limit as x goes to infinity of x over e to the x. How would you evaluate that limit? L'Hopital, take it to the L'Hopital. Take the derivative of the top, 1, derivative of the bottom, e to the x. So that goes to 0. The boundary term is just 0. And we just evaluated the integral of e to the minus x, that's just 1. So we get gamma of 1 is 1, gamma of 2 is 1. So every gamma is equal to 1. Gamma of 3 will be 1. Yes? No. Okay. Let's try it again. Let's look at gamma of 3. That's going to be the integral from 0 to infinity e to the minus x times x squared dx. Let's do things a little bit more generally. Let's look at gamma of n plus 1. That's going to be the integral from 0 to infinity of e to the negative x times x to the n plus 1 minus 1 dx. So integral from 0 to infinity e to the minus x times x to the n dx. So what should we choose for u? What should we choose for dv? So what would u equal? X to the n. dv would just be e to the negative x dx. V is negative e to the minus x. And du is just going to be n x to the n minus 1 dx. So we're going to get uv at 0 infinity minus the integral from 0 to infinity of v du. So uv is going to be x to the n negative e to the negative x at 0 infinity plus the integral from 0 to infinity of v du. So that's going to be n e to the negative x times x to the n minus 1 dx. The boundary term is just 0. We pull out the n and we get the integral from 0 to infinity of e to the negative x times x to the n minus 1 dx. Can anybody recognize what that integral is? That's our definition of gamma of n. How did we define gamma? Where is it? It's the integral of e to the negative x, x to the s minus 1 dx. What we just showed is gamma of n plus 1 is n times gamma of n. So let's record some things. So we have gamma of n plus 1 is n gamma of n. We know gamma of 1 is 1, gamma of 2 is 1. So here's n, here's gamma of n. 1, 2, 3, 4, 5. Gamma of 1 is 1. Gamma of 2 is 1. Gamma of 3, I can write 3 as 2 plus 1. So this is going to be 2 times gamma of 2. What's 2 times gamma of 2? It's 2, right? It's 2 times 1 or 2. I can write 4 as 3 plus 1. So this would be 3 times gamma of 3. Well, let's write gamma of 2 as 1. Well, because we know gamma of n plus 1 is n gamma of n. So if I want to calculate gamma of 3, if I know gamma of 2, I can write gamma of 3 is gamma of 2 plus 1 is now just 2 times gamma of 2. So I've got this formula, gamma of n plus 1 is n gamma of n. So I know each one by knowing its previous. So I can write 4 is 3 plus 1. So now if I take n equals 3, I get 3 times gamma of 3. Well, gamma of 3 was 2 times 1. For 5, I can write this as 4 plus 1. And so this is going to be 4 times gamma of 4. So 4 times 3 times 2 times 1. What does that equal? This is 4 factorial, 3 factorial, 2 factorial, 1 factorial, 0 factorial. Gamma of n plus 1 is n factorial if n greater than or equal to 0 is an integer. This function actually generalizes the factorial function. It is incredibly useful that we can actually write the factorial function as an integral. This allows us to very easily approximate how big is the factorial function growing. The factorial function is one of the most important functions in statistics and probability. When you're trying to estimate likelihoods of various events, you need to be able to understand factorials. So we are going to use this in tomorrow's lecture, which is Friday, to find the volume of the n-dimensional sphere. You know, the one-dimensional sphere, two-dimensional sphere, three-dimensional sphere, you should know these. So what's the volume or the area of the two-dimensional sphere, the sphere in the plane? What's the formula for a sphere? We'd call it a circle. Area of a circle is pi r squared. If we go to 3 dimensions, now we have a sphere. What's the volume of a sphere in 3 dimensions? Not 4 pi. 4 over 3 pi r cubed. In n dimensions, we know it's going to be an r to the n. But what is the constant? How does the volume of the n-dimensional sphere compare to the volume of the cube that it lives inside? If you think about what's going on in the line, you know, the sphere is the same as an interval. If you think about what's going on in the plane, you have a square. So we'll have over here, you know, n, the line, the sphere. Oh, I guess not line. I'll call it I'll call it box, the sphere, and then the ratio of the sphere to the box. So when n is 1, the length of our interval is going to be 2. The sphere is going to be 2. The ratio is 1. When we have a two-dimensional object, we have a square. What's the area of a square where the side is of length 2? 2 squared. And what's the area of the sphere? So I'm always choosing things so that the radius equals 1. So the box has sides of length 2. So what would be the area of the sphere that lives inside the box? It would just be pi. So the ratio would be pi over 4. It's about 75%. If I go to 3, what would be the volume of the box? 2 cubed. And then we said it was 4/3 pi. So the ratio is going to be 4 pi over 3 divided by 8. So it's going to be pi divided by 6, I think. So it's smaller. What do you think happens in the limit? What fraction of the n-dimensional box do you think is covered by the n-dimensional sphere? It went from 100% to about 75%. to a little bit more than 50%. What do you think happens in the limit? Yeah, it looks like it might converge to 0, that in the limit, very few points will be that far away. All right, so this is a good point to stop. And again, the goal for the last bit of the semester is to try to choose problems that will allow us to review what we've been seeing. So today, we were able to review some of our integration, we were able to review some of our convergence tests while getting results, which if you continue in math or science, you will need.